Today we have the 7th lecture in the course Artificial Intelligence. In today's lecture, we will talk about two-player search. In the last few lectures, we have looked at different formulations, state space formulations of some types of problems which were formulated as search problems. But in all these cases, we assumed that there is one agent or one machine who is trying to reach the goal from the start position. In today's class, we will consider situations where there are more than one agents. In particular, we will talk about two agent situations. In fact, a specialized two agent situations where there are two competing players, so that the gain of one player is the loss of the other player. So, we will see that such problems can be formulated as search problems, a different kind of search problems which has different characteristics than the single agent search problems that we considered earlier. But before we go on to today's lecture, I would like to discuss the questions of the previous two lectures. So, first let me come to the questions from lecture 5. Question number 1, suppose you have the following search space. The search space will be given to you in the form of a table. You are required to A, draw the state space of this problem, B, assume that the initial state is A and the goal state is G, and you have to work out a few search strategies and show the search tree and how and what sort of path the search generates from the initial path to the goal. So, this table gives you a representation of the state transition of the system. There are states A, B, C, D, E, F, G, and these are the edges A, B, A, C, B, D, B, E, C, 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 D, C, F, D, C, D, E, E, G and F, G, and in this column we have the costs of the different edges. In addition, for heuristic search, we will need to have an estimate of the cost at a particular state. So, the estimate at A is 8, at B is 8, at C is 6, at D is 5, at E is 1, at F is 4, and at G, which is a goal state, the estimate is 0. Now, given this state transition diagram, we have to work out different search strategies. In fact, 3 search strategies. Number 1, uniform cost search, number 2, greedy search, and number 3, A star search. And you have to show at each step of the search algorithm the node which is being expanded and the content of fringe. Also, you have to find out the eventual solution discovered by the specific search algorithm and the solution cost that is achieved. Now, let us go back to this table representing the transition. So, A to B we have an edge with a cost of 4. So, this is a graphical representation of the same table. A to B there is an edge with cost 4, A to C there is an edge with cost 1, B to D has cost 3, B to E has cost 8, C to C has cost 0, C to D has cost 2, then C to F has cost 6, D to C has cost 2, D to E has cost 4, E to G has cost 2, and F to G has cost 8. So, this is a representation of the state space for this problem. Now, let us quickly look at how uniform cost search works on this problem. So, if you recollect, in uniform cost search we start from the initial state and we expand nodes in the order of their distance from the initial state. So, from the state A, we can reach the nodes C and B. So, we put C and B in the so what we will do is that we will put the nodes, initially we will put the node A in the fringe or in the open list. This will be the initial content of fringe. At the next instance, we will remove this node from the fringe and expand it. So, A will be the first node that gets expanded, and as a result we will get its two children B and C, which we will put in fringe. B has a cost of 4 and C has a cost of 1. So, C and B will be put in fringe, C with a cost of 1 and B with a cost of 4. Now, at the next step, we remove the lowest cost node from fringe, which happens to be C. So, we remove C from fringe, expand it, and then find the children of C, which happen to be D, F and C itself. Now, C has already been expanded. So, if we keep track of it, then we will not put C in the list. Instead, we will generate D and F. D will have a cost of 1 plus 2, that is 3. F will have a cost of 7. And so, we will have D with a cost of 3, B with a cost of 4 and F with a cost of 7. Now, next we will remove again the lowest cost node and expand it, which happens to be D. After that, we will find the children of D, which happen to be C and E, out of which C is in the closed list if we do maintain a closed list. If we do not, we will put it in. So, let me not put in C right now. So, let me put in E. So, what we get is B, E and F. So, E will have a cost of, D has a cost of 3 plus 4, 7. So, E will have a cost of 7, then B is already there with a cost of 4 and F is there with a cost of 7. Okay. Now, out of these 3 nodes which are in the fringe at this instant, we will remove B, which is the smallest cost, and then we will find the children which happen to be E and D, out of which E is already there in the fringe, and the current cost of E through B would be 4 plus 8, that is 12, and E is already there in fringe with a cost of 7. So, E will not go into fringe, but D will, and D will have a cost of 4 plus 3, that is again 7. So, in the fringe we will have D with a cost of 7, E with a cost of 7 and F with a cost of 7. Now, we have to remove the lowest cost node. In fact, all these 3 nodes have the same cost. We can remove any one of them. Let us say that we remove D. So, if we do remove, but D is already been expanded. So, we will not put D and then we will remove E. If we remove E, we will have F left in fringe and E has the child G. Now, G will have a cost of 9 and F is there in fringe with a cost of 7. So, now next we will expand F, and F has no new child. F has another child G, which will have a cost of 15. So, we will not put it in here. Instead, we will keep G with the original cost of 9, and the next step, G is the only node in fringe. So, we will expand it and G happens to be the goal. So, we are done. So, you see, in this search we have expanded the following nodes A, C, D, B, E, F, G, right. And then if we broke this tie in other way, if we had expanded F first, then rather if we had expanded F first, then we might have got some other sequence of nodes. but once we get the goal, we can retrace and find the path. So, it happens that in this case G will have the parent as E will have its parent as D will have its parent as C, and C will have its parent as A. So, the path found would be A, C, D, E and G, and this path has a cost of 9. Okay. So, we have uniform cost search has found an optimum solution, and this optimum solution has a cost of 9. Okay. So, now let us now go and see what happens if we use greedy search for this problem. In greedy search, we start from A and find the node which is closest to A, or rather we find the node which is reachable from A and whose H value is minimum. Now, from A there are two nodes which are reachable, B and C. B has a H value of 8 and C has a H value of 6. So, what we will do is that we will take C, because C has a lower H value. Now, from C the two successors are D and F. D has a H value of 5 and F has a H value of 4. So, we expand F. So, we go to F. Now, F has one successor which is G, which has H value of 0. So, G is expanded. So, we get a path A, C, F, G, which is the solution found by greedy search in this case. What is the cost of the solution? It is 1 plus 6, 7 plus 8, 15. So, cost is 15. Obviously, in this case the greedy algorithm does not give you the optimum cost path. Now, next we will look at A star search, how A star works on the same graph. Now, in A star, first the fringe contains the single node A, then A is expanded and its children C and B are generated. C has a cost of, if you remember in A star, the F value of a node n is equal to its G value, that is its cost from the initial state, plus the estimate of its cost to the goal. So, for the node C, the G value is here 1 and H value is 6. So, C has a cost of 7, B has a G value of 4 and a H value of 8. So, B's cost is 12. Now, C is expanded, removed from open, and its children are C, D and F. So, C is already been closed. So, D and F are put in open, whose cost F value happens to be 8 and 11. Next, D is removed from open and its children are inserted, then E is removed, then finally we get G. As a result, we get the solution path A, C, D, E, G, whose cost is 9, and the nodes expanded are only A, C, D, E and G, which happens to be smaller, lesser than the number of nodes that we expanded in the case of uniform cost search on the same graph. Now, let us look at the second question. In the second question, you are asked to write the algorithm for bidirectional search using pseudocode. Assume that each search is a breadth first search and that the forward and the backward searches alternate, expanding one node at a time. So, this is a pseudocode. Fringe, we maintain two open lists, fringe 1 and fringe 2. Fringe 1 contains initially the start state. It represents the search tree as we move forward from the goal start state, and fringe 2 is the open list of the search tree which we get while going backward from the goal. So, while fringe 1 and fringe 2 are not empty, well both are non-empty, we first remove the first node from fringe 1, let it be node. So, if node is in fringe 2, then we return the path that we get from start to node concatenated with the path that we get from goal to node reversed. Otherwise, if node is not in fringe 2, we generate all successors of node and add the generated nodes to the back of fringe 1. If we are done, we go to fringe 2. We remove the first node of fringe 2, generate all successors of M and add the generated nodes to the back of fringe 2. So, this is the pseudocode for bidirectional search. Third question, give the time complexity of bidirectional search when the test for connecting the two searches is done by comparing a newly generated state in the forward direction against all the states generated in the backward direction one at a time. So, in bidirectional search, we have the start state here, we have the goal state here, we have a forward search from the start state, we have a backward search from the goal state until they meet, and when they meet, we get a path from start to this node n and from goal to this node n, and we concatenate them to get the path. Now, if the tree has a branching factor of b and if these two search tree generations alternate, these trees will meet about halfway. So, the depth of each of these trees would be d by 2. So, the number of nodes in this tree is b to the power d by 2, number of nodes in this tree is b to the power d by 2. So, total 2 times b to the power d by 2 nodes are expanded. But every time we expand a node in the forward tree, we check it against all the nodes on the backward tree, and the number of nodes in the backward tree in the fringe of the backward tree is of the order of b to the power d by 2. So, for every node expanded in the forward direction, we spend order of b to the power d by 2 time checking it against the fringe of the backward tree. So, total time taken is order of b to the power d. But bidirectional search can be made faster if we do not check every node here with every node in this fringe, but use some hashing scheme so that this test can be performed quickly. In that case, we may be able to get a performance which is nearer to order b to the power d by 2, which is square root of order b to the power d for plain breadth first search. Now, we move on to questions from lecture 6. Question number 1, compare ID A star with A star in terms of time and space complexity. So, let us assume a search tree with a uniform branching factor of b. If a tree does not have a uniform, so in this case, the time complexity of A star is b to the power n, of ID A star it is b into b to the power n. The space complexity of A star is b to the power n, of ID A star is only b into n, which is linear. However, if the tree does not have a uniform branching factor, this may not be true, but we can see that if A star expands m nodes, ID A star expands at most m square nodes. This happens if at every new iteration exactly one new node is expanded. Question number 2, is hill climbing guaranteed to find a solution to the n queens problem? The answer is no. Hill climbing can be applied to different formulations of the n queens problem, but there is no guarantee that for all values of n an optimum solution can be found. Question number 3, is simulated annealing guaranteed to find the optimum solution of an optimization problem like traveling salesperson problem? The answer is no. Simulated annealing reduces the tendency of the search being stuck at a neighborhood local minima. However, it does not guarantee that a global optimum is achieved. Now, we will move on to today's lecture, and today's lecture, as I have said earlier, is on two-player search. So, this is module 2, problem solving using search, and lecture 7 is two-player search part 1. The objectives of today's lecture: the student will learn how to formulate two-agent zero-sum games as a search problem. They will learn how to apply the minimax procedure to decide a move. They will learn how estimated payoffs are used when search to terminal nodes is not possible. Humans have always been fascinated with games. Games challenge our ability to think. So, people have been engaged in many different types of games. There are simple games that we play like tic-tac-toe or noughts and crosses. Then there are other simple games like Nim, Kala, 8 puzzle. And there are more difficult or more complex games like chess, Othello, bridge, Go, checkers. Othello is actually not that complex. Now, computers playing games. So, since the beginning of the history of computers or artificial intelligence, people have been fascinated by the idea of making computers play games. So, if you recollect, we discussed that Alan Turing conceived of that computers could play chess. In fact, the first machine to play chess, or first machine that claimed to play chess, go back many years. So, I forget the exact time, but it was, the machine was called the Turk. It was actually, it was a contraption which claimed to play chess, even though actually there was no intelligence involved in it, no machine like intelligence, because this contraption had a human hidden inside the interior who would play the moves. So, anyway, so since then we have come a long way, and today the chess program in 1997, the Deep Blue chess program developed by IBM, succeeded in defeating the world champion Garry Kasparov in a 6-game match. There are other games for which computers programs have been written like checkers. Checkers programs have been able to beat the human world champion. Backgammon. So, backgammon programs like TD Gammon by Tesaro have been written, and backgammon is actually a game of chance, involves the throw of dice, but backgammon program that like TD Gammon competes with the top few human players. So, it is very good, but there are human players who are also as good. In Othello, the computer program plays much better than the best human players. Then there is the game of Go, where unfortunately computer programs do not do so well. So, Go has a very high branching factor, and computer programs have not been successful in Go. So, human players are much better. So, we will consider a particular type of game involving two players, where the two players alternate, they compete, and both the players have perfect information of each other. There is no dice throw or any chance factor involved, and these are fully competitive games called zero-sum games, where the payoff of one player is exactly the negative of the payoff of the other player. So, they have exactly opposing interests. So, that is why they are called zero-sum games. So, this is like, for example, the game of chess, where if there are two players A and B, if A wins, B loses, if B wins, A loses, or A and B both have a draw. Now, let us see that game playing can be formulated as a search problem. We can take the initial position of the board. For example, in chess, the initial board can be taken as the start position, and the goal position is the position where the king of one of the kings has been captured. Okay. If you take the game of tic-tac-toe, the initial position is a 3x3 board with no cross or knot in it, and the final position is a position where either there are 3 crosses or 3 O's in a row, in a column or in a diagonal, or all the positions are occupied. Okay. Then successor function in a game search, game tree, defines the set of legal moves from any position. Like in a chess board, if white is playing, white has a number of possible moves. So, these are the possible successor positions for white. The terminal test determines when the game is over. In chess, the terminal test means when the king of one of the sides is captured. The utility function, when a game is over, the utility function gives an outcome of the game. For example, in chess, if white and black are playing, if white wins, we give white a utility of +1. If white loses, we give white a utility of -1. If white draws with black, we give white a utility of 0. So, the basic strategy in game playing is to grow a search tree. In game trees, in search trees for games, only one player can move at each turn. And so, we have a tree starting from the initial position to the successor positions and so on until we reach the goal position. So, at this level, player 1, it's player 1's turn to move. At the next instance, it will be player B's turn to move, then again player 1's turn to move and so on. At the leaf position, when the game is finished, we can assign utility to the player. For example, suppose the game is a simple game involving just win, draw or loss, we can give a utility of 1 to the winner, -1 to the loser and 0 to both the players if there is a draw. In games like backgammon, there is a concept of doubling or quadrupling. So, there is a concept of gammon and a backgammon. So, a normal win gets a value of +1, a gammon may get a value of +2, a backgammon may get a value of +4. So, there are games where the utilities are more. So, we can in general have a numerical value of the utility. Now, once we have the search tree, we can find out we know the utility of the leaf positions. We can assign utility to the leaf positions of the game tree, and we can propagate these values backwards to compute the utility of other nodes which are in the intermediate nodes of the tree or at the root of the tree. Okay. And we will discuss such methods. We assume that the opponent, you see, in the difference between single agent search and two agent search is that in single agent search there is only one player who moves at every step. So, we can plan the entire path for the player, we can find the entire path to the goal state. However, in two agent games, if I am one player, I can only make one move and then have to wait for the move of the other player. Only after the other player moves, then only I can plan my next move. So, I cannot plan the entire sequence of moves at a time. So, I can only plan one move at a time. And then depending on the move that the opponent makes, we make our next move. Now, we do not have any control on the move that the opponent makes, but for the sake of analyzing the worst case performance of these algorithms, we will assume that the opponent makes the move which is the best for the opponent, and because this is a zero-sum game, it is that move which is worst for us, which puts us in the worst position. And we will pick the best moves on our own turn and assume that in the opponent's turn, the opponent picks the worst move for us. So, this is a very simple example of a game tree. So, A is the initial position. It has the two possible moves to B and E. From B, the opponent can make a move to C and D, C or D. From E, the opponent can make a move from F to G. And from C, we can make a move to this position or this position. From D, we can move here or here. F we can move from here or here, G we can move from here or here. And these are the terminal positions. At the terminal positions, we have the following utility. At here we have a utility of -1, here we have a utility of 5, -2, -4, 1, -1, 2, 4. Now, since this is our turn to move and at C we have two choices, -1 or 5, we seek to maximize our utility. So, we will choose the move to this node whose utility is 5. So, the backed up utility value at C is 5. Similarly, at D we have two choices to move to -2 and -4, of which -2 is better for us. So, the backed up utility of D will be taken to be -2. At F we have two choices and one is a better choice than -1. So, the backed up utility at F will be +1 and we will move in this direction. At G we have a choice of 2 and 4, 4 is better for us. So, G will have a backed up utility of +4. Now, here at B and E it is the opponent's chance to move. So, the opponent has a choice of going to 5 or -2. The opponent will choose something which is worst for us. You see, if the utility is 5 for us, it means that from the point of view of the opponent it is -5, and at D from the point of view of the opponent it is +2. So, opponent will choose this move and the backed up utility at this node will be -2. At E the opponent has a choice of going to +1 or 4. It will choose this which is the worst for us and the backed up utility is +1. At A, which is our turn to move, we have a choice of getting utility of -2 or +1 and we will choose this because we get a better value of here. So, the backed up utility will be +1. So, you see we are assuming while backing up the utility values that at every step we make the best move and the opponent makes the worst move for us. And we guarantee that if we go along this path, the minimum payoff that we can get is +1. Okay. So, you see we are to compute these utility values, we are alternating minimization and maximization. So, here we are doing minimization at this layer where we play and we are doing minimization at this layer where the opponent plays, again maximization at this layer where we play. So, this sort of backing up is called a minimax algorithm. So, this is just the algorithms in action. These are the backed up values and A has a backed up value of +1. Okay. Now, so in two-player games, I will just repeat, we have two players alternating. It is a zero-sum game. There is perfect information where we know exactly what is all the moves are deterministic. There is no chance involved. The two players take turns and try. The max players, we call that player which tries to maximize the utility the max player, and the other player the min player who tries to minimize the utility function. We assume that the max player makes the first move. The leaves represent the terminal positions. Now, given a game, given the description of a game, we will draw a game tree. In the game tree, the successive nodes represent the positions where the different players may moves. A game tree could be infinite in size, right. So, there could be path which never leads to a goal state. And then some quick definitions. The ply of a node is the number of moves needed to reach that node. Suppose this is the root of the game tree, and then to reach a particular state we go through different levels. The ply is the number of moves that we need to reach the node. Okay. So, that is the number of, you see, to reach this node from the root we need to move along 3 arcs. Okay. And given a complete tree, the ply of a tree is defined as the maximum of the plies of its nodes. That is, the depth of the deepest leaf is called the ply of the game tree. So, first we are going to look at a brute force search algorithm to back off the utility function. And this brute force approach needs us to start from the initial node and generate the entire search tree up to the leaf positions, assuming that the game tree is finite. If the game tree is finite, we can reach the leaf positions in finite time, maybe, if we have sufficient space. And we will see how to back up the utility values there by the minimax method. However, for all but the most trivial games, the game tree can be extremely large, and it will not be feasible for us to generate the entire game tree. And then we will see how to decide the best move using some heuristic. But we will initially, nevertheless, we will initially look at the brute force search and then we will improve upon it. So, let us take an example of a simple game, 5 stone nim. So, this game is played with 2 players and a pile of stones. Suppose we have, let us say, 15 stones to start with. Each player removes a stone from the pile, each player removes either 1 or 2 stones from the pile, and the player who removes the last stone wins the game. So, this is the description of the game of the 5 stone nim, where each player can remove 1 or 2 stones at a time. Let us draw the game tree of this game. So, initially let us assume that we start with 5 stones. Now, at this position, the max player can move either 1 stone or 2 stones, giving rise to either 4 or 3 stones left over. The min player can remove either 1 or 2 stones from 4 or from 3. Again, the max player can remove 1 or 2 stones, etc. And then we stop expanding the tree until all the leaves have 0, that is, no stone left. And I have colored the nodes alternately by red and green. Red or pink represents the max player and green represents the min player. This is the max player and this is the min player. So, let us look at the leaves. The green leaves correspond to win for min. So, the payoff for max here is -1. The pink zeros, pink leaves represent win for max and the payoff is +1. Okay. Now, let us apply minimax to this tree. You see, let us look at this node. It has only one child, so its payoff will be same as its child, which is -1. This node has 2 children whose utilities are -1 and 1. This is a minimizing node, so the backed up utility value will be -1. At this node, the backed off utility value is 1. This is a max node. The backed off utility value is the max of 1 and -1, which is 1. At this node, the utility is 1. At this node, max node, the utility is max of 1 and -1, which is 1. At this node, the utility is min of 1 or 1, which is 1. At this node, the utility is 1. At this node, the utility is again 1, here the utility is -1, here this is a min node, utility is -1, max node utility is 1. So, for the max player, the backed up utility at this node is +1, and the best move for the max player is along this direction, that is remove 1's 2. Okay. So, you see at the max nodes, the max player needs to consider only the best move. At the min node, it must consider all possibilities, and it must make sure that for all ways in which min could move, max still has the best value. So, these min nodes can also be looked upon as AND nodes and the max nodes as OR nodes. Now, let us come to the Minimax theorem. The Minimax theorem states that every 2-person zero-sum game is a forced win for one player or a forced draw for either player. In principle, these optimal minimax strategies can be computed. So, if we have the payoffs at the leaves and we back this up, finally at the root we will get a value. That value can be either 0 or positive or negative. So, if the value is positive, if max plays judiciously, max can force a win from this position. If the backed up payoff value at the root is negative, no matter how well max plays, if min plays well and extremely intelligently, then min can force max's loss. Okay. If the payoff is 0, if both the players play at their best, this game would end in a draw. Now, if we just in the previous slide we looked at the game tree of 5-stone Nim, and we saw that it was a win for max. Similarly, if we draw the game tree of tic-tac-toe, tic-tac-toe is a game which all of you are familiar with. You have 9 squares and you play cross, the other player plays 0, you play cross, the other player plays 0, you play cross, the other player plays 0, and this is a win for min or win for O. So, in the game of tic-tac-toe, it is actually a very simple game, and you can see that the payoff of the root is 0. That is, you can force a draw. If both players are intelligent, you can force a draw. So, in minimax search, the max player selects the move that leads to the successor node with the highest score. Conversely, the min player selects the move that leads to the successor node with the lowest score. The scores are computed starting from the leaves of the tree and backing up these scores to their predecessors in accordance with the minimax strategy. In the minimax strategy, every node in the tree is examined. So, you start from the root, you examine, you back off at every intermediate node until you get the backed off value at the root. So, this is the pseudocode for the function minimax. So, function minimax at the node n, we are starting at the node n. If n is a leaf node, then we return the payoff value of this leaf, the estimated score of this leaf. Otherwise, if n is not a leaf, suppose n has m successors, n sub 1, n sub 2, n sub 3 up to n sub m. If n happens to be a min node, then we will return min of minimax of n1, minimax of n2, minimax of n sub m. Otherwise, if n is a max node, then we will return max of minimax of n1, minimax of n2 up to minimax of nm. So, this is the Minimax algorithm, very simple algorithm. This algorithm was invented by von Neumann and Morgenstern in 1944. However, the game tree for all but the most trivial games become extremely large. So, we cannot do exhaustive search, we cannot generate the entire game tree. The minimax strategy, as we described earlier, works when we can draw the entire search tree, but such trees can get big very fast, can get big exponentially. So, you know that if the tree has a branching factor of b, then if we look at a search tree of depth d, the number of nodes in the search tree is of order b to the power d. So, we have an exponential number of nodes, and so search trees grow very fast. So, if d is not extremely small, but d is reasonably large, then if b is more than 1, this becomes large very fast. For example, if you consider the game tree for chess, chess has an average branching factor which is estimated to be about 35. Chess games are often about 50 moves for each player, which means that the size of the game tree is about 35 to the power 100, which happens to be approximately 10 to the power 154, which is an extremely large number, inconceivably large number. However, if you consider not the search tree of chess, but the search graph of chess, in fact, in chess there are about 10 to the power 40 distinct positions, but even 10 to the power 40 is an extremely large number. So, we cannot enumerate the entire search tree for chess in any way. So, what we do instead is to use heuristic minimax search, where we search to some fixed depth, fixed cutoff, which is called the search horizon. And so, if we only expand the tree up to a limited depth, what will happen is that we will not reach the leaf nodes. And if we do not reach the leaf nodes at an intermediate position of, let us say, chess, we will not know whether it is a win for white or a win for black or draw for both of them. So, we have to estimate at the intermediate position whether it is good for white or good for black. So, we estimate the merit of positions at the frontier of the search tree by some heuristic static evaluation function, because we do not yet know the final outcome. So, after we make some moves, we have to decide, we have to know whether that move is a good move. And if we assume that, we can even apply the static evaluation function at this level. But if we assume that when we grow deeper in the tree, we can have a better evaluation function, we can expand the tree up to a cutoff, we can estimate the value of the boards at this depth, and on the basis of this estimate, we can apply minimax to find the backed off utility value at the root, and also which is the best move for the root to take. So, the modified heuristic minimax function will look like this: minimax at the node n. If node n has reached the cutoff, has reached our terminal test of where we want to terminate search, then we return the estimate of n. We call this the payoff. So, this will be an estimated payoff of n. Else, if n is a max node, then we set v equal to infinity plus infinity. If n is a min node, we set v equal to minus infinity. Then we find out all successors of n. For each successor m of n, if n is a max node, v equal to max of earlier value of v and minimax of m. Otherwise, if n is a min node, then V is min of earlier value of V and minimax of m. So, basically this is minimax of the partial search tree, where the search tree is only evaluated up to a certain cutoff, and the estimated value at this frontier is computed by some heuristics, and then minimax is applied on those estimated values. So, let us look at some examples of heuristic function. In chess, a lot of people have written lots of programs on chess. We will just mention one very simple heuristic that is used for chess. You see, how good a board is for a player depends on how many pieces the player has, but just the number of pieces is not enough. The type of pieces which are there are also important. So, in chess, the utility function could be the number of pieces on board of each type multiplied by relative values summed up for each color. So, we call this heuristic the material gain. So, we find out the material gain for white minus the material gain of black to compute the utility of white at a node. And the material gain of a white is the weighted sum of the pieces that white has, and each piece has a weight associated with it. Like a pawn can have some small weight, maybe the knight has a larger weight, and so on. So, this gives us an estimate of the board. So, a heuristic static evaluation function for a two-player game is a function from a state to a number which gives its estimated payoff. The goal of a two-player game is to reach a winning state, but the number of moves to reach that winning state is unimportant. So, the cost, the length of the path is not important. What is important is whether we can get to a winning state or the state with higher payoff or not. This is one of the differences with one agent search. So, if we have a heuristic static evaluation function, if we design a heuristic static evaluation function for a two-player zero-sum perfect information game, then we can use this minimax strategy to play the game. From any given position, we simply generate all the legal moves, apply our static evaluator to the position, and then move to the position with the largest or smallest evaluation. So, we suppose we want to find out the best move to take from this position. We find out all the successes, find out the evaluation of all the successes, and take the max of them and move towards that. However, static evaluation functions are not very accurate. So, instead of going only one level, we might go for several levels and then back up the values there. So, let us look at tic-tac-toe. So, in tic-tac-toe, we must have a function to detect if game is over. If x is maximizer, then the function returns infinity if there are 3 x's in a row, which is win for x, or rather +1, -1 if there are 3 o's in a row. And our static evaluation function is the count of the difference in the number of different rows, columns and diagonals occupied by x and o. So, we count the number of rows, columns and diagonal occupied by x minus the number of rows, columns and diagonals occupied by o. So, this is a tic-tac-toe search tree. This is the initial position, the max's turn to move. There are 9 possible successors, but since this is a symmetric, there are 3 different actual successors. For this one, the evaluation is 3 minus 0, 3. So, x occupies 1 row, 1 column, 1 diagonal, o occupies 0. Here x occupies 1 column, 1 row and 2 diagonals. Here x occupies 1 row and 1 column. So, the valuation is 3 here, 4 here, 2 here. So, this is the best move to take for x based on this one level of look ahead. This algorithm is very efficient, but it only considers immediate consequences of each move, that is, it does not look over the horizon. So, in minimax search, we expand the search tree further, look at further depth and then find out, suppose this looks at depth, one more depth and finds out the evaluation at this depth and uses minimax to back up these values. For example, this board has a payoff of 1, this is a payoff of 2. So, so this payoff will be min of 1 or 2, that is 1. And so, similarly we will just find out here the min is minus 2, here the min is 1 and here the min is minus 1. So, max will still move here because it has a payoff of 1. So, we search as deeply as possible and then use minimax. So, we will just stop with this last example of the minimax tree. So, this is a minimax tree with showing us the terminal evaluation functions. So, in minimax we will evaluate this node which is 4, this is 2, this is minimizing nodes, the blue ones are minimizing nodes, the green ones are maximizing nodes and then the final evaluation function is 4. So, we will stop here in this class. For the rest we will look at the next. So, we stop with questions for lecture 7. Suppose the game tree for a particular problem has a branching factor of b. If you do a p-ply look ahead and then apply minimax on this game tree, how many nodes will you expand per move? Question number 2. Consider minimax search on a game tree with p-ply search and another minimax search with a q-ply search. If q is greater than p, which one is better? Okay. So, we stop today. We will continue 2-player games in the next lecture. Thank you.